Hello, can everybody? Yes, I think everybody can hear me. Well, thank you for your introduction, Jan. And first thing I would like to say is, previous paper, Honglak, that was a great paper. It shows very nicely the potential of these deep models, which is perhaps something that should be kept in mind when you are listening to my talk, because while I will not be presenting some fancy application, I will be talking about an algorithm to train them. Restricted Boltzmann machines, as Honglak introduced, are often used as components of these deep architectures. And I'm speaking about an algorithm to train those. First, again, I'm not talking about classification or regression. I'm talking about modeling data density with Markov random fields. Now, restricted Boltzmann machines are one type of Markov random fields, but there are quite some others, and the algorithm that I'll be speaking about applies to all of them. Another important class of Markov random fields are those without hidden units, and the algorithm works well on that too. The learning for Markov random fields is gradient descent, usually, and the gradient consists of two parts. The first thing you should do is increase probability in those areas of the state space where you find your training data. And the second part is decreasing probability in those areas where you find samples from your model. This helps to keep the model under control, prevent it from assigning too much probability to random parts of the state space where there's no training data. The problem with all of this is not the first part, but rather the second, because sampling from these models is usually intractable. What we do instead is we use not samples from the model, but surrogate samples. Contrastive divergence, like mentioned, or a pseudo likelihood, which is similar. Start a Markov chain at the training data, then do a few updates, and the resulting state is treated as a would-be sample. And that is where we do unlearning. It's not a true sample, so you do not get the true likelihood gradient, but because it's in the right direction, it sort of works. As well, I guess we have just seen. However, there may be a way to do better to get more accurate samples. What I'll be mentioning now is something that I explained last year at this same conference in Helsinki, the persistent contrastive divergence algorithm. And it's inspired by this observation. Contrastive divergence does the unlearning in areas of the state space where the model assigns too much probability, but only areas that are close to your training data. So areas like here and here will be kept at low probability, but this one won't be. So that's how contrastive divergence is, in a way, inaccurate. There is a way to do better. And the central idea is to not throw everything away between gradient estimates. We do, as for CD1, use a Markov chain to get, well, either samples or as close to samples as we can get from the model. And different from CD1, we're going to keep it close to the true model distribution, to the equilibrium distribution. We are going to do a few transitions on these Markov chains after every weight update to allow the samples to catch up with the recent change in the model. But the new part is that we're not going to reset the Markov chains to the training data for every gradient estimates. That is what CD1 does, but we'll not be doing that. So we just keep the state of these Markov chains. That's why I call it persistent contrastive divergence. The idea is that this way, we always have samples from close to the model. If we wouldn't change the model at all, it would be exactly the model. We would have true samples after some burn-in period, because we would have a regular Markov chain. No learning, just the Markov chain updates, the Gibbs updates. We do a little learning with a small learning rate, so the Markov chain is never quite at the equilibrium distribution, but always just a little behind, and close enough to provide good samples. That's the idea of persistent contrastive divergence, and it works. Here is what you do in practice. You initialize 100 Markov chains arbitrarily. You initialize the model randomly, small parameters. And the optimization iterations are like this. You get your next batch of training data, and you estimate the positive part of the gradient using that batch. So this is where we're going to increase probability. And the negative part, the decreasing probability, that's what we're going to do wherever the Markov chains are at the moment, the negative data. We take the difference of these two parts of the gradients and we do a little learning on theta. After doing the weight update, we do an update on the negative data, a regular Markov chain update, Gibbs sampling, on whatever the model happens to be at the moment. So that's always a little different from what it was at the previous iteration. And as I said, it works, but we should take another look at what's really happening here. This is a slide that I had 3 slides back. The general idea, here's something we should take another look at. The philosophy is that we keep the Markov chains close to equilibrium, close to the model distribution. And that sounds nice and plausible, but it was not something that I had tested when I talked about this algorithm. To test it, well, the model is changing all the time. So if the Markov chains are to keep up, then they should have a decent mixing rate. So let's take a look at that mixing rate. What I did is I trained a restricted Boltzmann machine, a classification RBM, with one additional visible unit which represents not a pixel, but rather the class of the image that we're looking at. This was trained on the MNIST digits dataset, so there are 10 possible labels. And what I'm showing is the state of 96 Markov chains, because 96 fits in a nice image. On the left, I'm showing the state of the pixels, the pixel visible units. And on the right, I'm showing a histogram of the states of the label units. So the total is 96. And I initialize all the 96 chains with all the pixels off and all the label units saying that we're looking at a 0. We're actually looking at a black image. We're not looking at a 0, but that's what it says. And this RBM was trained for 3 hours with 40,000 weight updates. It gets decent classification performance, 1.6% errors. So it's a model like you might encounter. What I'm going to do is 10,000 iterations of the Markov chain, and I'm going to display the state after every 100. So you're going to see a 10-second video with 100 frames. And between each frame, there are 100 updates of the Markov chain. And again, as I said, the question is the mixing rate of this Markov chain what we'd expect it to be? Let's take a look. As you see, things are changing, as you'd expect, for a Markov chain. But they're not changing all that much. The label unit, most of the labels stay at 0. In the middle there were a few that switched to 2 for a moment and then switched back. And accordingly, the pixel units keep displaying 0 images. For all of these 10,000 Markov chain transitions. So this is not all that good of a mixing rate. We trained the model with 40,000 weight updates. So the internal persistent Markov chains saw 40,000 transitions, which they had to use to keep up with the changing model all the time. And afterwards we look at it, we give it 10,000 transitions, and we find that it does nothing. So something here is missing. Well, this is a Markov chain, as I said. It was, in fact, generated by a persistent contrastive divergence script with the learning rate set to 0. As I mentioned, that is a regular Markov chain. So here's something else I'm going to do. We're going to set a tiny learning rate. This model was well trained, but we're going to train it a little bit more. For another 10,000 weight updates, with a learning rate of 3 times 10 to the negative 5. Now, the original model was trained with a learning rate of 0.2. So this is really, really tiny. But it's not 0. So let's see whether there's a difference from what we saw on the previous slide with the 0 learning rate. What we see here is that it takes a while, but after a while, most of the chains go to something other than 0. They go to a fairly balanced set of digits, let's say. You see this in the labels, and you see this in the images. So with just this tiny bit of learning, the Markov chain, which is now no longer a regular Markov chain, but a PCD Markov chain, displays a lot more mixing. Let's try what happens with a bigger learning rate. Not much bigger, you know. The original learning rate was 0.2, so this is still small. Well, it just happens faster. You see again, now it takes a few thousand updates before we have a fairly balanced set of digits. See both in the histogram and in the images. Well, bigger learning rate. Takes 1,000 iterations to get something fairly balanced. And, well, the digits are mostly staying the same, but sometimes one changes into another, especially at the start of the whole iteration, of the whole sequence, when all those zeros have to become something else. Bigger learning rate. Much bigger learning rate. Learning rate of 1, which is bigger than what the model was trained with. No burn-in period to speak of. We just jump straight into a balanced set of digits, and quite often one digit changes into another. Pretty much on every frame, which means that in 100 Markov chain updates, you get a different digit. If you do this much learning, let's do some more learning. Learning rate of 3. Now that's an unhealthily large learning rate. It still works, but the digits have become a little bit fuzzy. And of course, they change rapidly because we have a large learning rate, and we've seen that larger learning rates cause more rapid mixing. Let's try a bigger learning rate. 10. Now we no longer get a meaningful model. This learning rate is too large. We still get a histogram of labels, but the images that we see no longer resemble digits. So what have we seen here? We see that without learning, the mixing for this chain is terribly slow. With just a tiny bit of learning, it gets decent, and with more learning, it gets better. The question is, how come? Well, to answer that question, we need to have another look at the PCD algorithm. Remember what we do with this negative data. We treat it as would-be samples from the model, and then we reduce probability wherever they are. The negative phase, unlearning. So after we've changed theta in this way, it's time for an update on the Markov chains. And what do all these Markov chains find? They find themselves suddenly in an area of low probability. They don't know that they themselves are the cause of that. They just see that it's an area of low probability. And what do Markov chains do when they are in an area of low probability? They quickly move to an area of high probability. So they quickly move away, wherever they can go. And this is what happens on every iteration. So this is the central slide of my talk. The learning accelerates the mixing. You unlearn on the state of your Markov chains, then you force them to mix. You make wherever they are low probability, so that they quickly move to another area of the state space. That's the central idea. And this is how you can get a Markov chain which intrinsically has a terrible mixing rate, you can make it mix very fast. There was a similar talk yesterday by Max Welling, Herding Dynamical Weights to Learn, and if you're interested in what I'm telling you, you should also come to his poster this evening. His paper was similar but had a deterministic learning. And also he claims that regardless however large you want to make your learning rate, it still works. So something is different about his story, because in my version you still need, not too large learning rates. So this is all interesting. We can make a Markov chain mix fast by doing learning. And by doing more learning, we can make it mix faster. Now, we all like Markov chains that mix fast because it allows you access to good samples from your model. So maybe you'd want to have very fast learning, but very fast learning, we've seen that. That has its drawbacks. There's a limit to that. So what are we going to do? Well, we're going to do both. We're going to do both fast learning and slow learning. Fast learning is going to take care of the mixing, and the slow learning is going to take care of the not going out of control. So we have the best of both worlds. To do fast learning, we also need a set of fast weights, which we have next to the regular weights. And we're going to make sure that they're always close to it. So we have two models. The fast model is going to take care of the mixing and provide good samples. And then the regular weights, the regular model is going to learn with a small learning rate using those good samples. Here's what it looks like in a computer program. You initialize, as before, theta to small weights. Fast theta is initialized to zeros. This part's new. You initialize negative data arbitrarily, as you did in PCD. Then an optimization iteration is, as before, you get the positive gradient on a couple of training data points. The negative gradient comes from wherever your persistent Markov chains are at the moment. We do learning using the difference of those two gradients on both of your models, both the regular and the fast model. And you do an update on the Markov chains using the fast model to make the Markov chains move elsewhere rapidly. And then you decay this fast theta a little, because the fast model is actually the regular theta plus the fast theta. So we do the Gibbs update on the model that you get from regular theta plus fast theta, and fast theta is always kept small. That's what this last step is for. When it's very small, when you have a zero fast learning rate, then you get back PCD. And as I said, the fast weights should have a bigger learning rate than the regular weights. The regular weights learn slowly to, not get anything terribly going out of control with noise in your gradient estimates. And the fast weights don't care about that. They just learn rapidly to provide good samples. And that way, the fast model is always jumping around rapidly around the regular model. The regular model is slowly learning. The fast model is jumping around it to provide samples, but always staying close. Now, I have experimental results, and I should say that it works. It works better than PCD. When you don't have time for lots of parameter updates, which is the case if you are short on time, but more importantly, when a gradient estimate takes a long time. So the situation that Hong Lak talked about, that's a large dimensionality, so gradient estimates take a long time. You don't have time for a lot of parameter updates. And my experience was that fast PCD outperforms PCD and things like CD1 and pseudo likelihood when you don't have time for a lot of parameter updates. So for a large dimensionality, this is an algorithm that looks quite promising. If you do have time for lots of updates, then it does about the same as PCD. Now this plot is classifying MNIST digits, and I did some other experiments. But the most important part of what I've been telling you is actually the theoretical explanation of what's happening with this learning, encouraging mixing. And that's what I would like you to remember from this talk. If you do want to see more results, I have them on my poster this evening. My paper is number 363. I think that should enable you to find it. So to wrap up, FBCD, fast BCD, is persistent contrastive divergence with fast weights, and it happens to, learn faster. And this is achieved by making good use of the fact that learning encourages mixing, but doing it in such a way that it does not mess up your model. Because we do it on a separate model that's there only for the fast mixing, but that does not, it's not the true model that we're talking about. The true model learns slowly with these high quality samples. And that's what I had to tell you today.